Jett. I've been working on the software for this since last year when I was in year 11.
I'm Lachlan. I've been working on the hardware side of things. I thought we'd go through a rundown of some of the pieces that are involved in this and how we're able to get them working to do what we want them to do.
So to start off, we have a controlling laptop. On there we have basically some ground control software and a live video stream. The live video stream is coming from this camera, which is connected to a Raspberry Pi, which is then connected to the network. And the laptop's also connected to the network, and when we send a movement signal, which is basically just, we have several values that will change based on this joystick. When the values get changed, they get updated to the Raspberry Pi, which in turn sends it to the Pixel, which controls the motor controller and has GPS inputs.
Yeah, so of course then the motor controller interprets that pulse width modulated signal and outputs into 4 different motors.
Lachlan's rover must be able to negotiate the college terrain with ease, including significant gradients of up to 30 degrees. To choose appropriate motors for this unit, we must consider a worst case scenario. Motors are under highest load when traversing a slope. The torque demanded from each motor must overcome both acceleration due to gravity and the frictional force on the ground, while still accelerating the rover forward. We can calculate the vector component of apparent horizontal acceleration due to gravity at a 30-degree gradient in the diagram. The rover must be able to navigate the college with a reasonable speed of 25 km per hour or approximately 7 meters per second. So therefore, 116.66 radians per second is our angular velocity for the motors. To find the power needed for these motors, we use the formula power equals torque multiplied by angular velocity, and therefore we can find the power equals 30.2 watts. This allows us to actually order the motors from the supplier to the exact specifications for the job.
The frame of this was designed in AutoCAD. We firstly made a 3D model, just laying out where all of these components would fit. But once we confirmed that those would be appropriate, we made some prototypes with MDF and the laser cutter. And our final model is this acrylic transparent frame.
The camera is also on a full gimbal, which allows us to look around while we're moving, instead of a fixed position camera, which would severely limit our navigational capabilities. And so this is our ground control software, and it interfaces directly with our joystick, and our joystick will update a set of values we have. You can see them changing here, which then get sent over UDP to the Raspberry Pi, and that runs over the wireless network. Our ground control software, Mission Planner, allows us to also get a GPS fix. The GPS is mounted on our rover here. So what we can see here is a live video feed from our camera right here. It's completely movable as well. The live video feed was a huge challenge for us, as we needed to find a way of sending video that was both efficient in terms of network and extremely low latency, as that was required for driving it without direct supervision. So what we came up with was GStreamer, which is this specific program designed for streaming video at a low latency. And that gave us 30 FPS 720p video, which is extremely good quality for both this camera and for the low latency which we have, which we can roughly guess is probably under about, what would we say, a quarter of a second, as a clap will happen almost immediately on the camera.